is a continuation of
Okay,
the
dear
previous
colleagues,
ones.
let's start out today's seminar.
Sorry, say it again, please.
It is yet one more talk. Yes, it's a continuation of Professor Shabat's talk about his about introduction to the sound. Okay, let's proceed.
Okay. Thank you very much for the possibility to give this talk. Formally, it is a continuation of the two previous ones, but in some sense can be understood independently. So today we start with the BLE pairs, the concept of a BLE pair over an arbitrary ground field K that we assume algebraically closed, and a BLE pair is a pair of a curve for x over k and a rational function on this curve that is non-constant, and graphically, as soon as we understand the function as a branched covering of the projective line here, we allow its branching only over 3 points in the projective line, like this arbitrary branching, or maybe no branching, over these 3 points, and no other. I will not draw it graphically, sorry, but I'll give a formal definition in a while. Maybe I give it now in the algebraic way. So whenever the differential of beta in P is 0 or infinity, then it implies that the value of beta in P belongs to one of the 3 special values. This is the formal definition. Now we can mostly forget about the ways of drawing BLE pairs that we have discussed in the previous lectures, though we are going to actually draw BLE pairs, but it will be clear from the context what do we mean by the graphical interpretation of a BLE pair. And now let us give some technical interpretation of it. Sorry, after I I better remind that in case when K is C, then we have the topological model of X as an oriented compact surface. And on the Riemann sphere, where we mark the points 0 and 1, in several ways we consider the graph. Maybe I use another color. The graph, I can't reach color. Oh, yes, I know how to do that. The color, perhaps let it be green, and its pre-image then is a green graph, and we are going to draw it. 0 is the point. Well, there are several restrictions on the branching, but they will be reminded perhaps in the process of discussion of the results. So the problem is this pre-image is the sun, and the main problem today that we are going to address today is the actual calculation of the association Billy pair to a descent that we are going to call the calculation of a descent. Well, another traditional expression when the genus of the curve is positive, the normal thing is also that the problem is to calculate the defining equations. So it is a problem in constructive mathematics, and it is hard, and I would say non-traditional in the sense that as a source we have some combinatorial object that can be defined by certain finite amounts of information. And this is what we have discussed during the first lectures, though today we are going to understand it quite informally. I mean, we are going to actually draw the descents. And the target is another constructive object. So now I remind that according to Billy theorems, these objects are defined over Q bar, the field of algebraic numbers. I mean, that means that the curve itself can be defined by the equations with the defined defined by the finite amounts of information, but of information of very different kind. And then perhaps I speak about the most exciting part of this constructive mathematics, uh, but Control P, as you taught me, well, it doesn't. Well, Control P should make my pen active.
Excuse me, can you remind me what is X and what is B? Beta.
X is a curve over any field, but today we are considering the cases of the field of complex numbers um, and the field of algebraic numbers. And beta is the shorthand for Bialy pair. That is the function of this restricted branching. And now I have a new technical problem, unable to, oh yes, it is. Okay, then. Then perhaps before turning to the actual no, I cannot find the colors of pen. During the last seminar, Control P worked, Control Pen perhaps, but it does not work now. Tools maybe. Can anybody help me? How do I use the pen? So the reason is
Excuse me,
I can.
excuse me, Professor. Can you see the left hand? There is a list, try, and you can see it.
No, I cannot. I don't see it. Maybe additional
Maybe you
entity.
can stop reshare. Maybe you can
Should I
reshare.
stop the sharing now?
Y- Yeah, I think you can stop reshare and stop sharing and reshare.
Yes, let me try that. But I can. mm, um, I don't have it either. Oh, yeah. Now I have the full screen. Maybe the trouble was that I was not in the full screen mode. Now I have an empty whiteboard, but with all the tools that I can use. So maybe I proceed from here, just not to lose more time. So do you see my whiteboards? Then let me give now the formal definition of the Bialy function in terms of divisors. So the divisor of the beta itself, that is the sum of its zeros and its poles with the multiplicities, positive for zeros and negative for poles. So the divisors of beta itself is the sum of zeros denoted like this. So alpha is the number of zeros, and then gamma is the number of poles. That's it. And then there is a restriction for the divisors of beta minus 1. Then we have maybe k is a better index here. And here we have the sum up to n. Well, it is easier to give the definition for what was called the clean case. And I remind that pictorially it means that over 1, all the branches are twofold. Then there is the divisor is twice the sum of some points. With of course with the same negative part. 1, 2, gamma. And then we'll have a complete algebraic definition of a Abelian pair. If we add to it, we consider the differential of d beta and add that it is its support is just the set of all the points in the previous formulas, and it is the sum of I from 1 to alpha, but of course all of a I minus 1 a sub j. Here I just mean that we know what happens with rational functions under the differentiation. And then the b points, the points over 1, add the simple sum b sub j to n. And we know what happens to the poles of a rational function under the differentiation, and the negative 1 is added here. And what we know from algebraic geometry, that there is a restriction on the on all the multiplicities, and so the whole degree of the divisor of d beta that can be calculated from this expression is, as we know, 2j minus 2, where j is the genus of of the curve x that has been introduced. Now, there is kind of a Moscow term that will be especially important in our consideration, the passport of a PLA pair.
Excuse me, it's not written not clearly. 2g minus 2, then do you put a bracket? Do you multiply? Or so
2j minus 2, what do you mean? 2 times j?
times, or should you put brackets or multiply 2 by genus or what?
2
Just
by g, I mean the usual order of algebraic.
by g, it's clear, but
2
then
times j minus 2.
yes. So what you write on the right, you do not multiply it by anything. So just the Euler characteristic, right? So
No, I
you write
multiply
2
2 by j.
minus.
Well, since
Oh, so 2j minus 2, and then the words genus of x are not
oh,
in this.
genus of x is sorry, I better uh, circle the j. J is the genus of x. Yes, thank you. Now I see. So can I proceed? Did I
Sure,
answer this question?
sure.
Okay, so there is a passport of BLA pair. That is just the table of multiplicities. This I'll explain in a while why I prefer to write it. Oh, sorry, to write it vertically. A sub alpha, then 2's that in some cases can be replaced also by arbitrary numbers, and C1 sub 1, C sub gamma. The whole, this may be not quite a matrix before, since it has 3 columns of different heights. And I write it vertically just to remind the picture of the covering, where we have perhaps a sub 1 here, a sub 2 here. This is over 0. And similarly, or the other two branch points. Now, maybe what should be specially stressed, that the whole information is contained in these two equalities. And as for divisor, it is just for checking. And we see that only the passport is used in them. So maybe I'll write it in a bit more detail. So given the sun, maybe let's write in terms of all the sets of the objects. Our goal is to reach BLE pairs. But the calculation, the result is reached through taking into account only the passports of the covering, not more delicate geometrical information of the dessins. And now, since I'm short in time, I just formulate two open problems with respect to the passports. Which one are realizable? The ability. This is a very open question, sometimes called the Hurwitz problem. So it can be considered without any reference to algebraic geometry. And so if the other problem is then if the passport is realizable, what is the number of realizations? So these are the purely combinatorial questions, and now I return to BLE pairs and to arithmetic. First of all, I introduce the one of the possible notation for the absolute Galois group. That is the group of automorphisms of the field of the break numbers called an absolute Galois group. So it is a profinite group. It means that it is projective limit of finite group. Topological, it is a topological group. Group and well, is absolutely disconnected, like the Cantor set. And this group is quite mysterious. Perhaps I can claim that it is observable only by its finite factors. Better write it in words. By finite factors. And there is a famous so-called inverse Galois problem. given a finite group J, does there exist a subgroup, a normal subgroup in the absolute Galois group whose factor is J? The positive answer exists for lots of classes of finite groups, but the problem itself is highly open. Now, what is the relation of this object and the problem, inverse Galois problem with what we are discussing? The relation is as follows. Gamma acts in the obvious way over. Sorry, I did not introduce this obvious notation of Bailey pairs over Q bar, just acting on the coefficients of the equations and on the coefficients of the Bailey function. And it is more or less obvious that under the action of the Galois group, the pair remains the Bailey pair. Well, basically because the multiplicities, the valences of the graph embedded into the surfaces are just the multiplicities of zeros and poles. So it turns out it results in the construction that fascinated Alexander Grothendieck mostly. So there is some action of the absolute Galois group of dessins that, at least theoretically, gives the unique possibility of visualizing the Galois group besides the possibility of visualizing the only element, the complex conjugation. That is, of course, realizable by taking the mirror image of any element. Now, since I'm rather restricted by time, perhaps I turn to the examples of what has been calculated and will present some ready materials for that. The first piece of information like this is the certain amount of catalogs. The first one in 1990, perhaps one, is by Alexander Zvonkin. Betrema. And Pierre Rea with all the plane trees with no more than 8 edges. And it is still available in the internet. Then, in the beginning of our century, about 3, it was a group of my seminar, lots of other participants, all the dessins.
So if you have unsolved problems or problems your students are working on, it would be great if you establish some communications. And I think some people from our seminar may join.
Thank you. I think it
at
is
least
a very good. Thank you. It's a very good idea, and perhaps after my talk we discuss the possibilities of its realization. Thank you. So, with a number of edges, at least 4. So this is really done, and maybe I draw the most difficult one. That stopped us for a couple of years. Difficult one was the torus, realized like this, with the identification of the opposite sides and a small pen in one of the angles. Well, and then a couple of others.
I remember, excuse me, I remember I listened some lectures by Zvonkin, and he told how to use the song in order to get, for example, Mathieu group.
I have prepared the materials for that. You'll see it in a while.
Okay, great.
Okay, and now perhaps just one example here with the famous name, but before that maybe. So sorry, somebody is speaking. Sorry, can you say it clearer or write down?
Someone should turn on off the microphone. I apologize. It's not me, but someone should turn off the microphone. Excuse me.
Now we'll have I introduce a very interesting class of plane trees of diameter 4 in an obvious sense. Diameter 4 that we denote, say, a sub 1, a sub k. Diameter 4 means that there is a central versus, and here we have the vertices of the corresponding valences, and nothing more than that. A K here. And now I give the historically first non-trivial example called Leila, because of the famous mathematician Leila Schneps. But the name is Leila's flower. It was just the 4, diameter 4, 3, 2, 3, 4, 5, 6. We can try to draw it. Here is 2, and here is 3, and here is 4, and here is 5, and here is 6. So quite a simple flower. Then the Galois orbit. No, maybe I won't write down the passport since it is obvious. Well, let's call it Lila flower. And the Galois orbit of Lila flower could be expected to be 24. It depends on the cyclic order of these lepels. So we can cyclically order them in, 5 minus 1 factorial ways. But it is wrong. It is not so, and it consists of two Galois orbits. I'm writing this in quite a symbolical way, and the elements of one orbit are gotten by the permutations only of only by the even permutations. So we can take this one, this tree, plain tree as it is drawn here, and apply all the 12 even permutations to it, and then take another half of the orbit. And the corresponding equations are very complicated. The case can be covered only with rather advanced computer calculations, but the two halves turn out to be quite similar. And we know lots of other examples like this up to now, but we do not have a complete explanation. Now, perhaps before we turn to more advanced, to the plane trees related to Mathieu groups, let me say some words about positive genus. So, what are the examples? Well, maybe the two simplest toric examples are can be understood without any calculations, just because of symmetries. Here, X is defined by the equation like this, and beta being x square, and if we realize the torus by the identification of the opposite sides of the hexagon, then we get, I prefer to write it in the Fermat form, and beta y square. And this is a particular case of the Fermat, say, M n x to m plus y to n is 1, and beta, then one checks that beta is either x to the mth.
Excuse me, I'm afraid we can't see your screen.
Oh,
Can
you
you move
don't?
it?
Let me try to
Ah,
move it.
ah,
Is it better now?
I think it's better. Yes.
Good, thank you. Then one more class of examples and one particular example. Then there is an official term, curves with many automorphisms. They were studied in the 19th century with lots of mathematicians, and the definition is that the cardinality of a set of automorphisms is at least 8 times j plus 2j, as usual, is the genus of the curve. And then the theorem tells that they are the pairs x and
Excuse me. Why do you write x uh, uh, slash x x палочка и x? Почему
oh,
так?
it is just the way to mark 19th century. No geometry here.
Okay.
The pair is non-deformable, rigid. So it cannot be included in the non-trivial family together with automorphisms. And then the factor of x over the automorphism group is rational. I can avoid writing the ground field here because it is valid over any ground field. But what is more important is that the factorization over the complete groups is a Bely function. And by the way, soon we are going to have the 115th anniversary of Descent d'Enfant, since Klein's the first Descent d'Enfant was Klein's picture for his famous quartic. I'm writing it in the projective coordinates. And a very beautiful descent. Descent can be found in mathematical analysis, and you don't need to know lots of German just to enjoy this picture, the corresponding descent. And at the same time, it was the birth of the uniformization theory, because Klein has drawn it over the universal covering of it. And now perhaps the last example, called again of the group with lots of automorphisms, the Bring curve. So it lives in P4 and is given by a system of equations, say x to j plus y to j plus z to j. We need 5 letters, while
So
j
excuse me,
1, 2, 3. So it is a system of 3 equations. You could ask, so it sits in the hyperplane in projective 4 space, so you could ask, why don't write it as a space curve? The answer is that its automorphism group is precisely S sub 5, that permuting coordinates. Sorry, it seemed to me that there was a question, was it?
no. Well, I understood everything.
Okay, and then there is formulas for, let it be, say, bring and bring over factorization not over S5 but over A5 by some reason, corresponds to quite a famous descent. Let's call it the spoiled icosahedron. And the explanation is as follows. We take the usual icosahedron with all the with 5 edges incident to any vertex, and well, to turn it into a descent, we have to define the cyclic order. But we spoil, at every vertex, we spoil this cyclic order, taking not the next one, but just skipping one. Here is the cyclic order that you apply to the graph of the icosahedron, and it turns out that you obtain precisely the Brink curve. So I have shown you some examples of nice descents in the positive genera. Well, they are very special. They are related to the most symmetric curves. As for the general curves, the calculations are much harder, and I don't speak about them today. Now I'm going to switch to the prepared demonstration. for the trees related to mature groups. And therefore, we should discuss the questions, if any, on this whiteboard now. So any questions about what is written in the whiteboard? No, yes. So then I close it and try to share, not this one, but try to share the prepared one, and still I don't know how to get rid of this of the suggestions to share something. So perhaps I go to screens, files, additionally. Nothing like that. Any advices?
You click the share.
Yes, this
and
is what I have done. I clicked.
yeah, and then there is a screen in the upper part. There are screen, file, more.
Screen.
So
Yes,
you may
this is
choose
what I'm pressing screen now, but
and then there is they show several things.
but unfortunately,
desktop.
oh, there is another maybe. No, there is just a simple screen. So
Oh yeah.
I'm stopped. Maybe I didn't stop it properly. So now I need number one here, perhaps try to find number one, and it doesn't work yet. Maybe I leave the conference and return.
I think we just wait a little bit because usually it takes some time to share the screen.
Sorry, say it again, please.
We just need to wait. To share the screen takes time, so let us wait a little bit.
Okay, so we try just to wait, yes. If I heard you correctly. So we're waiting a bit. It was really suggested before, at the beginning of the talk. No, it is all the same.
Then
Drawing documents. Well, the only solution I can suggest is that I leave the conference and hope to return in a while.
Yeah.
Okay.
Sure.
This is just a thought, and I'm going to demonstrate just two pictures from it, because it would be difficult to reproduce them. So here is the plane tree. We're going to speak about now. What I did not tell you is that any plane tree has a natural bicolored structure. So the vertices are black and white in such a way that neighboring vertices are colored differently. So this is some, what you see is some tree of 11 edges. And now there is another object that I better explain here. ER is the abbreviation of edge rotation group. So this group acts on the set of edges, and it is just generated by two permutations: the contrary clockwise rotation around the white vertex with some fixed points, as you see, and the contrary clockwise rotation around the black ones. Now, the fact is that we were very much fascinated in 1995. We, the group of 4 authors, that exactly for this plane tree, we get the Mathieu 11. And we argue that it is maybe the simplest and quite a visual definition of the Mathieu group. In fact,
Excuse me, what about the monster group? Actually, Conway was excited with lots of groups corresponding to lattices. So Mathieu, and then
yeah. Well, I don't think there is any chance to visualize anything related to the monster group, since its cardinality, well, it takes half of the blackboard to be written down. So we cannot see the objects of that. Well, the cardinality of Mathieu groups, Mathieu 11 is also of several thousands, but it acts on a small object, small and visualizable object. What I have read many years ago, that there was a conjecture by Hertzbruch that monster is the group of automorphism of some manifold of dimension 24. And I don't know what is the current state of this conjecture. So unfortunately, we can, using plane trees, we can realize just 2 Mathieu groups out of 5. And with the dessins of genus 0, M24, the third one, M24, the 2 more, the 12th and the 24 has been realized, but it is out of today's talk. And well, I'm afraid that I'm saying nothing about the calculation of it, but let me say it orally. It is not at all easy to calculate the what is called Shabat polynomial, the Belay function corresponding to this tree. And if you just take all the set of trees with the same passport, then you'll get 20 something plane trees, but only 2 of them, this one that which you see and its mirror image, have this edge rotation group. And sorry, I'm afraid I haven't said that the edge rotation is the Galois invariant. Therefore, the others are defined over some huge fields of algebraic numbers, and there is no chance in writing them down explicitly. And we have looked at all of them and understood that our vision now is quite restricted, because we don't see any reason why this one is remarkable. Sorry, perhaps it would be more clear if I've drawn another one. But when we turn to the other Mathieu group, it will be a bit easier. So here is another more involved part. So there are 4 plane trees with edge rotation group, Mathieu 23rd. These 2 ones and their mirror reflections. So from the next slide, we see that there are more than 60,000 realizations of these trees and their field of they are defined over the field of unthinkable complexity.
How can it be related to the work of Maciejewicz? Which part of
let me see, perhaps we can turn to that slide. Here it is, sorry for the number. So Maciejewicz has computed the corresponding Shabat polynomial, and it was an interesting story because me, myself, and my 3 co-authors, we've covered the combinatorial part of it, and we were totally unable to calculate the Shabat polynomial. But Maciejewicz asked us whether it would be really interesting to see it explicitly. I'm not presenting it here, but the field is presented in blue. And Maciejewicz, after getting the positive answer, Maciejewicz has created some software just to get the answer. So from the point of view of today's lecture, the situation is as follows. We take the passport of these trees. Well, what are we going to see here? 3 fours. Yes, we see 3 vertices of multiplicity 4, several 2s and several 1s. Quite an innocent one. And it is realizable, but it is realizable in more than 60,000 ways. So potentially the Galois orbit is of that size. But among them, something very special takes place that singles out these 4 trees. And for them, we calculate everything. So this is one of the perhaps most striking results of several decades of the calculation. Now, perhaps I'll use no more written material and no more slides, but try to formulate one open problem. So in order to, so the only way, sorry, somebody is speaking now.
no.
So the only way that we are aware of now to calculate the field of definition is to calculate the Shabat polynomial. And in this case and in some others, it is an incredibly difficult task. First of all, from the point of view of just calculations. But as you see, there we twice see the number 23, and the field of definition of these ones is the biquadratic field, some extension of q of the square root of -23, and the general problem is how can it be guessed, or maybe even the easier problem is how to guess or, well, conjecture something about the field of the discriminant of the field of definition. And now Vasily Olegovich has suggested some kind of cooperation between the students. And I think it is one of the possible topics. Just starting with the experimental mathematics. I mean, analyzing the already calculated cases and try to understand the discriminants of the fields of definitions combinatorially. So 23 is the number of edges, and in the same way, in the previous slides, I didn't write it down, but here the Shabat polynomial is defined over q of square root of -11. In fact, this is not quite just these discriminants are not 100% mystical, because there is some relation of this irrationality. We can find all these irrationalities in the character tables of the groups of edge rotations. And the theoretical explanation of it, not in terms of descent d'enfant, but in terms of monodromy groups, which is just something more general, can be found in the Serre's classical book Topics in Galois Theory. But I don't think that the study of the systematical study of discriminants was performed. And my last suggestion, maybe also for some students' activities, is the problem of reduction of Belli pairs. As I have written on the whiteboards some time ago, the equations for Belli pairs are can be written down just in terms of the passport, and can be considered over any field, including the fields of finite characteristics. Well, we have assumed that our ground field is algebraically closed, but so the corresponding Belli pairs are defined over the algebraic closures of the finite fields, but actually they are defined over some finite fields. And it is not so difficult to understand that over almost all primes, the combinatorics of the Belly pairs is the same, but for some finite primes, say the edges collide, and we call such primes the primes of bed reduction. For the dessins of positive genus, these are the primes over which the genus of the curve becomes smaller. So the similar problem, perhaps related to the previous one, is to understand the primes of bed reduction from the combinatorics of the field. So this is another kind of obvious topics for the beginners. Sorry, again, it seems to me that there was some voice. Was there?
Yes. Yes. Recently, we had a very beautiful talk on group theory about Gründer-Kegel graphs for some groups, and there were
About what
some
graphs? Sorry.
nice
Say it again. About
Grün-
what graphs?
Grünberg-Kegel. So this is
Greenberg. Okay. Yes.
yes, this is some graph related to orders, prime orders of elements, how they are related, and this know a lot about this group, and I think maybe reduction at primes might be related to combinatorics of Grünberg-Kegel. I'm not sure, but
Well, I
maybe.
think it's a very very nice conjecture. Maybe it's not very general. Maybe the relation can be established at least in some cases, but anyhow, it's very interesting. Anyhow, I stop here and thank you for your attention, and we have a couple of minutes for the questions.
Okay, thank you very much. That was a really great talk. Are there any questions or comments? Yes, I would be happy if you send me some a list of initial papers or books we can read. You mentioned Grothendieck
Okay,
book.
we'll discuss it. Sorry, what I did not demonstrate here, and I can send these slides to somebody, and there is here there is some reference, a list of some references.
Okay, yeah, and then I will write an email, and everyone interested will. So yes, and it will be great if you tell me maybe your present or former students who are working, and yeah, we have such project called Seminar Friendship. So and it would be
Very good,
great
very
to
good. Yes,
yes.
we'll think about
Yes.
we'll think about it. I have planned a small course of 4 lectures, of which we had 3, and hopefully in May I'll tell you about the relations of Descendant-Fang with the geometry of moduli space of curves.
Okay, thank you very much. Any further questions or comments?
Okay, then I leave it, and thank you again for listening, and all the best. Bye.
Thank you very much. It was great.